Hey everyone, and welcome to The Explainer. I am so thrilled to have you here today because we're diving into a genuinely fascinating topic. If you've ever stopped to wonder how modern vehicles, which, let's be honest, are basically just supercomputers on wheels at this point, manage to function flawlessly without constantly crashing, well, you're exactly in the right place. Today, we're demystifying the AUTOSAR Classic Platform. We're going to break down exactly how modern vehicle brains are structured and figure out how the invisible software running our cars actually makes perfect, logical sense.
To keep things moving, here is our roadmap for today. We're taking a top-down, zoom-in kind of journey. We'll start with Section 1, meet the AUTOSAR Classic Platform, move into Section 2, unpacking the layered architecture, hit Section 3, deep dive basic software, look at Section 4, the runtime environment, and finally wrap up with Section 5, key benefits and applications. Let's just jump right in.
All right, Section 1, meet the AUTOSAR Classic Platform. Let's get our macro view of the whole automotive software landscape. Before we really get into the weeds here, we've got to ask a fundamental question. How does a modern car's brain actually work? Think about it for a second. A modern vehicle has dozens, sometimes literally hundreds, of electronic control units, or ECUs. You've got an ECU for the engine, one for the brakes, the wipers, the steering. It's a lot. And these are highly resource-constrained computers that require incredibly strict real-time and safety standards. Like, if you hit the brakes, the system can't just freeze up to load a background update, right? Now, in the old days, every single supplier wrote custom software for custom hardware. It was just total chaos. The industry desperately needed a way to manage all this complexity safely. Which brings us to the ultimate solution, the AUTOSAR Classic Platform. Basically, this is a standardized software architecture that was specifically designed for these embedded ECUs. Its main goal is to move the whole automotive industry away from that custom, non-scalable chaos and into a clean, standardized ecosystem. It gives engineers a structured, layered approach to develop, integrate, and, this is the big one, reuse software components across completely different vehicles and suppliers. Okay, let's dive into this big picture view. The AUTOSAR Classic Platform acts as the perfect standardized bridge. Way up at the top, you have your application software. That's the specific logic that tells your car, say, to deploy an airbag or adjust the climate control. And down at the very bottom, you have the microcontroller hardware, the actual physical chips inside the powertrain, chassis, and body ECUs. AUTOSAR is the critical middleman here. It sits exactly between the application and the hardware, making sure they can talk to each other perfectly without having to be completely custom-built for one another. Moving right along to Section 2, unpacking the layered architecture. Now that we know what it does, let's peel back the layers of this cake to see exactly how it's built. You'll notice right away that this platform is defined by a very strict hierarchy, flowing logically from top to bottom. Step 1 is the application layer, which is made up of software components, or SWCs. That's your high-level logic. Step 2 is the runtime environment, or the RTE. Step 3 is the basic software, known as the BSW. Step 4 is the microcontroller abstraction layer, which we call the MCAL. And finally, Step 5 is the physical microcontroller itself. So, the key takeaway here is this. High-level application logic starts at the top and absolutely must cascade down through these specific, standardized layers to eventually reach and actuate the physical hardware down at the base. Section 3. Deep dive basic software. Let's zoom into the absolute engine room of this architecture. The basic software, or BSW, is packed with distinct service modules that essentially do all the heavy lifting for the ECU. First, you've got system services, which manage the overall ECU state, watchdogs, and timers to make sure the system doesn't freeze. Then you've got memory services, managing non-volatile memory and RAM abstractions. You have communication services, taking care of complex routing through COM and interfaces like CAN or LIN. And finally, I/O hardware abstraction, which handles the control of all your various physical sensors and actuators. It's just a massive, completely standardized toolkit. Now, what's really interesting here is the clear distinction we're making between the basic software and the microcontroller abstraction layer right beneath it. Why go to the trouble of separating them? Well, look at the MCL. Its entire job is to deal with the messy, specific details of the physical microcontroller hardware. Because the MCL completely handles the physical hardware, it frees up the BSW above it to remain completely hardware independent. This means your basic software services remain standardized no matter what specific physical chip you happen to be using on the factory floor on any given day. Let's actually see how this all comes together by tracing a real communication signal all the way down the stack. Imagine the application software component at Step 1 decides it needs to send a signal. Let's say, just to turn on a light.
It sends this command to the RTE at step 2. The RTE then routes it into the basic software at step 3, passing right through COM, PDUR, and CANTEEP. Then it hits the CAN interface at step 4, and finally reaches the hardware-specific CAN driver down in the MCAL at step 5 to physically send out that electronic pulse. We've literally turned what looks like a wildly complex wiring diagram into a simple, standardized 1 to 5 journey.
Section 4, the runtime environment, or RTE. To really understand how the application talks to the basic software, we need to explore the super vital translator layer. The runtime environment, or RTE, is basically the glue holding this whole shebang together. It provides the communication between the software components at the top and the basic software below. But here's the thing, it does way more than just route messages. The RTE actually guarantees timing. It ensures data consistency for the application layer. It makes absolutely sure that when a high-level application asks for data, it gets it reliably, completely independent of how the underlying BSW is actually implemented. And this brilliantly illustrates how those application components actually interact with each other. Software components encapsulate your application logic. They are the most basic units of software. But they can't just talk to each other however they feel like it. They have to utilize standardized ports via the RTE. You have provided ports and required ports, basically acting as senders and receivers or clients and servers. So whether software component A is trying to talk to software component B, or whether a component is asking the BSW to save something to memory, it all flows completely seamlessly through these strict standardized RTE ports. Finally, Section 5, Key Benefits and Applications. We've seen how the architecture works, but what is the ultimate payoff of having this complex standard? Let's take a look. First off, let's look at where this platform actually lives in the car. Honestly, it is everywhere. It's in the powertrain and chassis, which are governed by incredibly strict ISO 26262 functional safety standards. It's in your advanced driver assistance systems, your ADAS, and safety features, which require rigorous ISO 21434 cybersecurity compliance to prevent hacking. And it runs your body, comfort, and energy management, all built on robust operating system standards like OSEC VDX. AUTOSAR isn't just a polite suggestion for developers, it's a rigid framework that allows engineers to meet the absolute highest global safety and security standards out there. To summarize the core benefits of this whole ecosystem, we're getting a layered, modular, scalable architecture that absolutely guarantees real-time, deterministic behavior. And because it standardizes all the interfaces, you gain massive tool and vendor independence. But listen, if you take away just one single thing from this explainer today, make it this: complete hardware independence. This architecture literally allows automotive engineers to swap out physical microcontroller chips, maybe because of supply chain issues or a hardware upgrade, without having to rewrite a single line of their high-level application software. That level of portability and reusability is an absolute game changer for the industry. Which leaves us with a pretty massive thought to chew on. We are fully entering the era of software-defined vehicles, right? Millions of lines of code are now dictating everything our cars do. The scale is just massive. So as these vehicles become even more incredibly complex, how will foundational standards like AUTOSAR continue to evolve? How are they going to bridge the gap between traditional embedded systems and the high-performance computing of tomorrow, all while keeping our roads safe and our cores future-ready? It is a wildly fascinating space to watch. Thank you so much for joining me for this explainer, and keep learning.